packet pushers.
Welcome to the IPv6 Buzz, where we dare to dive into the 128-bit address space wormhole. I'm Ed Horley.
And I'm Scott Hoag. On the show, we discuss all things IPv6, strategy, design, deployment, and operations.
And I'm Tom Coffeen. We've spent 20 plus years working with the IPv6 protocol. We run a consulting firm where we get IPv6 working for our customers.
And we're here to share some lessons learned and how to avoid common mistakes. We're glad you joined us. Today, we're going to be talking about neighbor discovery as part of our IPv6 basic series. And we just wanted to cover it as a fundamental, I guess. We talk about it at a high level, you guys, right, of what encompasses neighbor discovery and maybe some analogies to IPv4, because I think neighbor discovery is probably one of the more confusing things that we first talk about with IPv6 with many of the folks that we do training with. This is probably the area that people get the most overwhelmed with, right? Because it doesn't have a good analogy in some ways with IPv4 until you go through it enough times where maybe you're like, oh, I get what's going on.
Yeah, and there are more moving parts. And so I think we've decided that we'll cover some of those in later episodes, the basic series that we're doing. Today, I think, as you say, a high-level approach and maybe give you some conceptual handles to grab hold of what IPv6 neighbor discovery is in comparison to, what you're used to with IPv4.
Yeah, and just to set the stage of what we're talking about, this is a node on a LAN discovering another node on the LAN. And in order for two nodes on a LAN to talk to each other, they have to share a link layer protocol like Ethernet type 2. And so a node may know the v6 address of the other node, but then it needs to learn the link layer address of the other node to be able to send a frame to it. And so it needs to discover for the nodes to be able to talk to each other. So that's why we call it neighbor discovery. They're neighbors on the same logical IPv6 subnet, and they need to be able to talk to each other, and this protocol stitches that together.
Yeah, that's perfect. So I guess let's talk about what's encompassed inside of neighbor discovery, because it actually covers quite a few things. And this is just a convenient bucket of labels for everyone in terms of like grouping things together. So when we say neighbor discovery, it covers a sort of an array of things that go on that were all grouped together on, I guess, technically under an RFC, right, in terms of grouping these things together. And we've got router advertisements and router solicitations as one group. And I think that per Tom's comment earlier, we're probably going to cover router advertisements as a separate show, just because there's just so much going on there alone, right, that it sort of warrants its own discussion. But just realize that when someone talks about neighbor discovery, it is inclusive of router advertisements or router solicitations.
Yeah. I kind of refer to that as router discovery versus neighbor discovery. I know it's not delineated in the RFC, but I kind of think of them as two separate functions. A node learning about their local router, or the router communicating information to nodes that have joined.
Right.
Or neighbors talking to each other. And those neighbors, any node, as we talk about in IPv6 vernacular, a node is any device on an IPv6 network that has an address.
Right.
And a router is a type of a node that is doing packet forwarding. But a router is a node. It's one of the members that is connected to that network.
Yeah. So the router advertisement, router solicitation, we'll parking lot that and take that up as another show. But the next portion is exactly what Scott was talking about, which is nodes talking to each other, or neighbor solicitation and neighbor advertisement. These are how nodes on a given LAN segment would discover or find each other and be able to communicate back and forth. And there's some caveats around how some of this works that's definitely different than IPv4. And maybe we talk now really quickly about sort of the comparison so that people can maybe hold, I guess, an analogy in their head as we're talking through these sort of concepts. So I think probably the most obvious one that we all talk about regularly is like, hey, this looks a lot like ARP and reverse ARP, right? In terms of functions that you see in IPv4 land, where we're trying to map a layer 3 address down to some sort of layer 2 function, right, of Ethernet. And how do we get this to work back and forth? And so we have to use ARP and reverse ARP in order to be able to do those functions in IPv4. But due to some clever work in IPv6, we don't need anything that looks like ARP per se, in terms of a separate functional protocol portion that's working on the wire to make that glue happen. We're actually able to make all of this glue work with just native layer 3 addresses and also ICMP version 6 with multicast.
Yeah, because we kind of like forget the technical, I wouldn't really call it technical debt, but there are definitely some operational risks associated with ARP based on the fact that it's operating at layer 2 broadcast. And of course, not super efficient. Basically, I've got a broadcast that goes out on the wire. Everybody has to listen to it. Every network interface has to, grab that broadcast and pass it up the stack to see, is this traffic that I'm interested in, or, that's indicated for me, or can I ignore it? And of course, there's processing time and cost associated with that. Anybody who's been doing this for a while has been around to watch a broadcast storm bring a network to its knees, as they say. And so, as you point out, there are some efficiencies here that we're going to leverage in IPv6 neighbor discovery, where that layer 2 broadcast goes away and we've replaced it with some multicast functionality, right?
Yeah, because with address resolution protocol, node A knows node B's IPv4 address, but doesn't know the link layer address. So it sends out a broadcast like, everybody out there, who is this? What is your MAC address? And all nodes who get that broadcast are forced to process that packet, whether they wanted it or not. Everybody is forced. That's the term, broadcast. It's one to many, but it's forced. Everyone must process it, whether they wanted to or not, or whether it was intended for them or not.
Yeah, it's like that annoying couple that is doing a marriage proposal at a giant concert, and the poor guy on the stage has to like holler back and forth. So like, is this intended for you? But, and everyone else has to listen. You're like, oh, we don't care. Go away. We just want to hear the music.
Yeah,
That's
exactly.
right.
Yeah.
So I think those are helpful in terms of sort of understanding where neighbor discovery in general fits in, which is all about, and let's be specific, this is all happening on a local link of some type, right? You share broadcast medium, or this is a way for us to discover each other on a shared, wireless network, wired network, whatever other WAN-based transport you might be utilizing. But this is for us to get one node to the other node, whether that's a router or whether it's two hosts that exist on a network. That's really where it's focused. No part of neighbor discovery is really helping you get across a layer 3 boundary, I guess, is sort of my point, right? It's really all about finding localized resources. And that's why we want to talk about the router advertisement, router solicitation stuff separately, because that's all about how you find your default gateway, et cetera, et cetera. Neighbor solicitation, I guess we should start off with the ICMP version 6 type, which I think is 135, and then neighbor advertisement, which is type 136. And I guess we should talk a little bit about maybe why they chose the order of neighbor solicitation and then neighbor advertisement, right? Like, because you would think like, oh, well, I'll just advertise on a regular basis and people can find me. But the reality is you don't want to be that chatty on the wire. So I think the neighbor solicitation coming first makes sense. It's like, hey, I want to find someone, and I can provide a neighbor advertisement also on a regular response basis if need be on the wire. But more than likely, I want to wait for someone to try and find me. The way they're going to find me is utilizing more than likely DNS, right? To find my IPv6 address to be able to communicate to me, right?
Yeah. The solicitation is like the query, and the advertisement is the reply.
There's a reply saying like, hey, I'm the person you're looking for, right?
Mhm.
It's definitely the shout response sort of configuration on the wire, but we don't interrupt everyone on the wire because we're using ICMP version 6 with a specific set of addresses, right, to be able to accomplish this. So maybe we dig a little bit into that. We don't have to go into gory detail, but talk a little bit about like how we go about actually making the neighbor discovery process work.
Yeah, and I think one of the key advantages in the design of neighbor discovery and neighbor solicitation and advertisement is the presence of a valid self-configured layer 3, unambiguous, unique layer 3 address from boot time, essentially, which we don't really have that in IPv4. And so that becomes the part of the foundation by which these nodes are discovering each other based on the fact that they can unicast their unique link local address. I don't want to say unique. That makes it sound like a ULA. We're definitely not talking about ULA.
Gosh, no.
Yeah. But that link local address, that unicast link local address, that's essentially the foundation for communication between nodes starting from boot time.
Yeah, because with IPv6, we don't have any broadcast type message. There's no subnet broadcast. There's no all ones broadcast of any type. IPv6 uses multicast for all one-to-many communications, and it's efficient by its very nature. And so when the solicitation is sent, it's going to a LAN-based multicast destination that is only going to a subset of the nodes, or maybe really only the node that has the one address it's interested in. So it's more efficient in that regard.
Yeah, so let's talk about that part really quick. This is the vocabulary lesson part of the podcast.
Mhm.
So that destination address that we're talking about has to have some special bits, the last 24 bits from the address we're trying to get to, and then we make a special multicast address out of that. And basically, we're listening on the wire for that particular address. If anyone's addressing anything to it, it will interrupt its process to listen to it. So it's not guaranteed to be globally unique from a link local address perspective or a global unicast address perspective. It's not guaranteed to be unique, but the likelihood that you're going to have the last 24 bits of two addresses be the same out of 2 to the 64th is a pretty small number.
Mhm.
So there's not as much fear of having overlap. So you don't mind interrupting the few number of hosts that might actually build this address. And that address is a solicited node multicast address. It's a special designation. I can't remember the RFC 9131, something like that, I'm guessing. But that actually helps you build a solicited node multicast address. That is the multicast address you know you need to listen to if someone's interested in talking to you, right? Besides, obviously, your link local address itself. This is the whole purpose of the solicitation portion, is that the person who's trying to solicit you doesn't know your address, can't map it through, but does know to send something to a multicast address. And that's how it gets a destination address to send it to versus sending it to a broadcast address, right? That's the part that we're correcting there, correct?
Yeah, and there's a little footnote there associated with what I mentioned earlier of having that link local address that's configured at boot time. That's unicast address for that node that's self-identifying with. So another little thing that happens under the hood that we don't really generally take a look at unless we're sort of poking around where we don't normally poke around is there's a multicast group represented by that solicited node multicast address that you mentioned that uses that 24 bits that you mentioned, the lower 24 bits of the MAC address. And that's when that link local address is self-configured, there's an automatic subscription to that multicast group. And you can actually see this on a node. If you're poking around and looking at multicast groups that you're subscribed to, you will see that solicited node formulation of FF02:1:FF, and then those lower 24 bits that will, what does that match to? The link local address.
Yeah, it'll match both your global unicast and link local, assuming you have a global unicast address already.
Yeah, if you have that configured. This is our future show where we talk about router advertisements and the prefix information option, learning that prefix and creating a global unicast address. But if you have both those address types, then there'll be that multicast, solicited node multicast group that you're subscribed to listen for queries that are coming for those groups. And as you say, greatly isolating the number of nodes that are actually listening, not having to rely on broadcast and passing a broadcast up the stack and wasting all that time and processing power, relatively speaking.
Correct me if I'm wrong. The hot limit is also set to 255, so this can't go across any layer 3 boundary. And basically, you're just doing a query. You're asking through the neighbor solicitation, like, what is my other host link layer address? That's what you're really trying to figure out, right? That's the glue. Your v6 address, I need to glue it to a link layer address, your Ethernet address, in order to be able to send forward frames back and forth between the two nodes. And then the neighbor advertisement, which is the response, is really just the glue portion that says, like, hey, I heard that you were trying to reach me, right? And I'm going to unicast a response back to you and tell you, hey, this is me. And by the way, by doing that, you automatically get my link layer address. I knew your link layer address because that came out as that ICMP version 6 type neighbor solicitation message. So your link layer address was included as part of that. And I can respond back. And by responding back, you automatically get my link layer address.
Yeah, here's my digits.
Yep. Yo, here's my digits. We can now text. Yeah, that's the glue. So basically, this looks like, ARP, right? I mean, it functions in the same way in terms of being able to glue those layer 2 to layer 3 information sets together so that we can talk on the wire back and forth with each other without any issue. And so that's the sort of holler on the wire, get a response back, and now we know about each other. But the good news is we didn't need some intermediate solution to be able to make this happen. In other words, we didn't need ARP or reverse ARP to make the process work. We were able to do this all with layer 3 and with multicast and ICMP version 6. And that's sort of slick. That's definitely a huge optimization versus what IPv4 was able to do, and just basically be able to avoid all that broadcast related stuff that we were dealing with all along. So you're not as susceptible to broadcast related issues or even multicast related issues because the likelihood that you're going to have a solicited node multicast address that's the same for all the different nodes on the network is pretty close to 0. So you're just not going to have that sort of impact.
That's right. But the protocol does check for that, right? That's a duplicate address detection.
That's probably a good segue over to talk about duplicate address detection, because that's also a bit of what goes on for neighbor discovery. I don't know. How do we want to talk about that?
Well, I guess we can talk about IPv4. When there's a duplicate address, Like, oh, there's a lot of density in the address space, and oh, you tried to ping an address and it didn't respond, and so that's the address you assigned to a device. Uh-oh, there's a duplicate. And when in IPv4, when two networks on the same LAN segment share the same address, it's a collision, and both are negatively impacted by that address. They both have the exact same address. Who is the real 192.168.1.10 or something? If they both share the same address, it's a huge collision. And so in order to avoid that with IPv6, using this same method of doing a neighbor solicitation, you check first to make sure that your address that you intend to use is unique, as Tom says, and doesn't collide with anyone else. And so IPv6 is very polite in that way, where it checks first before it starts to use the address on the interface.
And as we say, if it finds a duplicate address, then you have DAD issues. So many people running their IPv6 networks. The risk of having DAD issues is low, as you say. But when DAD issues happen, well, we all know what happens. That can be pretty grim, which is why we have optimistic DAD, right?
Let's pause for just a moment to tell you about Human Infrastructure and Packet Capture, two weekly Packet Pushers newsletters you can subscribe to for free. Human Infrastructure delivers informative technical blogs, links to tech resources and tools, plus IT news stories and new product announcements, all with commentary by the Packet Pushers. There's also Packet Capture, a weekly digest of everything the Packet Pushers have published over the past 7 days, including podcasts, blogs, and YouTube videos. It's an easy way to find the episodes and content you want. Sign up for one or both for free at packetpushers.net/newsletters. We don't sell or share your email address with anyone. It's just between us.
Yeah. DAD issues would not occur if the interface identifier was random, either through privacy or temporary address, or even if you were using EUI64 informed your interface identifier using parts of your MAC address. Two hosts unlikely to have the same MAC address, although it does happen. But if both nodes had statically assigned their address and both chose the interface identifier like : 2, for example, with the router being : 1, two servers on a LAN both were statically assigned : 2, a low and easily known address, then they could collide potentially.
Right. So let's talk really quickly about what happens there. Let's say I'm the first host A, I come up with : 2, and then Scott goes in and didn't realize that I had set up : A, and maybe it's in the process of rebooting. So it's like, even if you tested it, you would be like, oh, there's nothing there.
I didn't look in the IPAM. I just went ahead and configured my own device rogue.
Yeah. And then you went in and you're like, we'll set up a new server, and here it is, it's server B, and I set up : 2, and then mine comes up, yours is rebooting, and then yours comes back up. What's going to happen? What's going on there? What's the process that's happening?
Well, my node is going to send out a neighbor solicitation with a part of its address that it intends to use in that multicast. And if it doesn't hear a response back, then it'll go ahead and use the address. If your node is up, Ed, then your node will answer back like, no, I'm using that. Please don't use that address. Here's my MAC address, actually, and I'm here.
Right.
Don't use that address. Then I'll be like, oh, it'll actually kind of shut down the IPv6 interface, because it'll say, oh, I had a duplicate address detection failure, so I'm not going to bring up IPv6 right now. And I may see an error message, or I see indication that DAD failed or something when I look at my address and wonder why IPv6 isn't working.
Right. And you'll get a message that basically says like, hey, there's a duplicate address detected. And I think this is important as a caveat. This is really when we're talking about like statically configuring something. The likelihood you're going to have this happen, like Scott mentioned, with randomly assigned addresses out of 2 to the 64 space is close to 0. But let's say you were the random lucky person who selected an address that's exactly the same as someone else on the network. Like the miracle happens and you do that. The reality is that your host will see it's got a duplicate address versus someone else who's on the wire. So my host A replies back to you and says like, hey, I'm using that address. If you're using Slack and you can just generate yourself a new address, there's no reason for you to have to shut your interface down at that point. You should just generate a new one and pick a new one and go, and then do a duplicate address detection on that one and see if you fail.
And then go buy a lottery ticket.
Exactly. Because you got hella lucky. Well, I don't know. You used it all up with that random address.
Yeah, you did.
But
we're sounding dangerously ignorant about how probability actually works here. But
yeah, I know.
that's fine. This isn't a math podcast. So.
But yeah, just realize that this is something happening behind the scenes. Now, there are timeout thresholds for how long, and you're supposed to not use an address until you go through the duplicate address detection process as a default. And we've mentioned in previous shows that Microsoft does something a little different with Windows. They do something called optimistic DAD, which is the likelihood that you're going to have a duplicate address collision is really, really small in a fraction. And so they want to start using the address right away. They still do a duplicate address detection check. They just don't do it as the first thing immediately. They get started with a bunch of other processes.
They don't wait for the response before they just
Right.
jump right in and start
Yeah.
using the address.
Yeah, and so that's the optimistic part of it. Or maybe we can just say that's more careless, free-spirited way.
Fun dad,
And,
not homework dad.
too funny. That covers duplicate address detection. And we talked about the Solicited-node multicast address. That is also used here for the duplicate address detection process. So it's important when you're just sort of understanding that Solicited-node multicast addresses are really a on-link local thing. It's just a tool to allow us to be able to discover things, and it's used by all of the neighbor discovery process. It's a very common thing that you're going to see occurring there.
Yeah, these are just administrative protocols that run behind the scenes. There's nothing you have to configure here. It's automatic. It's built into the TCP IPv6 stacks of the hosts and the routers. It's just something that is an administrative protocol that runs behind the scenes, allowing communication on a LAN, but nothing you have to configure.
Really, the best way to learn this is to set up two hosts on a LAN and set up Wireshark, and you can watch the set of traffic that pass back and forth, right?
Mm-hmm.
That's probably the easiest way to sort of see like, oh, I understand what's going on now. And you can walk your way through those packet walks to sort of get an understanding of what's going on there.
Yeah, just open up Wireshark, start listening on the interface, and then type in ICMPv6 into your display filter, press return, and you'll see only ICMPv6 messages, and you'll see these.
Yes.
Yes, we'd be remiss if we did not also just mention in passing the unspecified address and its role in all this, which is kind of unique, I think. We don't typically see a formulation such as the unspecified address. When you're popping the hood on IPv6 to check out how neighbor discovery is working, neighbor solicitation, neighbor advertisement, when you see a initial neighbor solicitation go out for address resolution, I think this is correct, and correct me if I'm wrong, but that will be sourced from the unspecified address.
Yeah, because you don't have an address at that point. You got to check to see if the first address that you want to use is available. So you have to put something into the source address, and it's all zeros.
It's all zeros, yeah. That's that whole part of the duplicate address detection, right? Before you can start using something on the wire, including link local address. I guess we should mention that. Hey, we'd be remiss. You also do this for your link local address. So the first time that you bring your interface up and you want to use your link local address that's probably being self-provisioned by the host OS, it does this duplicate address detection for the link local address to make sure no one else is using that link local address on the wire. So that definitely has the unspecified address as the sourcing address, because you don't have an address. You can't use your link local address yet. So you need to check, and that's how you do it.
Yeah. What also makes neighbor discovery more efficient is the timers tend to be longer. With IPv4, typical ARP timers are like 5 minutes. Pretty short, and nodes are sending those broadcasts kind of frequently, which also contributes to those broadcast storms Tom mentioned. But with ICMPv6, with IPv6, the neighbor cache expiry timer can be longer. It could be 14,400 seconds. I'll do the math for you. It's 4 hours. So they can be kind of long sometimes. They could be shorter. They could be longer. Could be as high as 65,536 seconds, which would be really long. But yeah, they can tend to be longer and not as short as just 5 minutes.
That's a good point. One thing we forgot to do, we forgot to tell everyone why we were stitching layer 3 to layer 2, that the multicasts, actually, there's two different buckets of sort of fitting in. For one of the reasons that we want to use a multicast address for that solicited multicast is so that we can use multicast at layer 2, right? To stitch that together. So you're going to see layer 2 multicast addresses in use to find each other that have that lower portion of the 24 bits encoded in it, which is super useful. It matches all the way up from that layer 2 to your multicast address up to your layer 3 address. Those last little bits are going to match all the way down. So that's sort of an efficiency thing. And I guess the layer 2 multicast address that you want to look for in terms of a preamble is the 3333. That's a designation for the multicast v6 address being encapsulated inside of an Ethernet frame, right?
Yes.
You'll see the 3333. And the only reason we want to mention that is because there's some really cool articles that the audience can go check out that we'll link in the show notes from Denise Fishburne. Denise was a guest on the show way back. What was it? Show 20? want to say a long time ago, but
My goodness, yeah.
yeah, demystifying IPv6 protocol analysis with Denise. So she covers exactly this, and yeah, it's pretty cool.
Yeah, Fish is brilliant, and that article is fantastic.
Yeah, it's definitely worth a read. And it really is all about that. And she's in the past has given a bunch of Cisco Live presentations on and going through exactly this material. So it's definitely worth checking out. I don't know who's teaching that these days, but you know, if you get a chance to pull up older Cisco Live material, it's well worth the time to sit there and listen. Cool. Well, thanks everyone. We'll get back to you with another basics talking about the router solicitation, router advertisement as sort of the next one in queue. Thanks for joining us for this episode of IPv6 Buzz. If you've got feedback or a follow-up on this topic, send us a message at packetpushers.net/FU. We'd love to hear from you and continue the conversation.
Also, on packetpushers.net, you'll find a range of deep dive technical podcasts for IT pros, including heavy networking, heavy wireless, and day 2 cloud.
There's a whole lot more on the Packet Pusher site as well, such as tutorial videos and a networking job board to help you find or fill your next great role. So whether you're deep in your career or just starting up, Packet Pushers is the place to go to grow both your skills and your personal network.
So long and until next time, we'll see you on the IPv6 internet.